In this video, we'll discuss the beginnings of calculus and other related topics. Now, while we teach differentiation first, integration was originally developed because it was used to determine the area under a curve, the volume under a curve, and the arc lengths of curves. Then we used differentiation. Its development came from determining maximum and minimum points as well as the tangents to curves. And originally, the two were not recognized as inverse operations not until the late 1600s. Now, when we look at the development of calculus, the Greeks used a method of exhaustion in trying to construct regular polygons that could have the same area as a circle. Archimedes used the method with parabolas and came relatively close to formulating a form of integration. Then we fast forward to the 1500s, where Regiomontanus translated some of those works of Archimedes, and others such as Stevin tried to avoid these methods of exhaustion and instead would use things like limits. Kepler took Archimedes' other method, which is a little bit simpler, and said that a circle is just a regular polygon with an infinite number of sides. And he was able to create his laws of planetary motion using this method of having an infinite number of congruent triangles that would then create that circle. Now, as we step forward, Bonaventura Cavalieri was another famous mathematician that had huge impact on pre-calculus. He studied under Galileo and had many works in mathematics, optics, as well as astronomy. Now, his work of geometry advanced in a new way by indivisibles of the continua came up with his principle that if two plane figures have equal altitudes and if sections made by lines parallel to those bases and at equal distances from them are always the same ratio, then the areas of those figures will have that same ratio. He also then proved that that is true for volumes of two solids as well. So what does this mean? If I take these two shapes here, say a rectangle and then this shape that has curves, the rectangle I can find the area for. Now, if I recognize that their bases are parallel to one another, and then if I take an infinite number of slices through this, and those slices always have that same ratio, that means that the ratio of their areas would have to be the same, which in this case would be 3 to 4. So I could calculate the area of the rectangle and then use this ratio to determine the area of the curve on the right. Now, when we think about differentiation, it's due to the work of Kepler and Fermat that we start to see advancements in the 1600s. Kepler recognized that there's these increment of functions becomes extremely small as it approaches the ordinary minimum and maximums, and Fermat then expanded upon the method that Kepler described. Here he would say that you have a minimum or maximum, and that we would then subtract this infinitesimal e from the function, and then we would solve it for x. And by making e virtually become 0, we're able to then determine the ordinate of the maximum or minimum. But we don't know whether this is a maximum or minimum. Now, we can graph these functions now, but back then it would have had to take a lot more of an effort to do so. But it did help determine that placement of the maximum and minimum. This work eventually did lead to how we think about defining a derivative such as the limit as h approaches 0. Now, other famous mathematicians that helped lead us towards calculus include John Wallis, who was a professor of geometry at Oxford for over 54 years. He's considered one of the first to explain and consistently use fractional exponents, which was immensely important as we look at integrals. His work in 1655 was able to show how to calculate an integration, not necessarily with the methods of what we use for integration now. Additionally, his works were able to show the use of the infinity symbol, as he would have to deal with these infinitesimals, as well as he's constructed with creating number lines for negative and positive numbers, as well as conic section equations to the second degree, thinking about that through an analytic geometry lens. Additionally, at this time was Isaac Barrow, who was a professor at Cambridge until he left to become the royal chaplain. He was one of likely Newton's professors at that time in the 1660s, and he recommended Newton to take his position when he left to become the chaplain. His work, Geometrical Lectures, focused on finding the lengths of curves and areas bounded by them, as well as the tangents to them. His work also showed the idea of the differential triangle, which is very close to the method we use for differentiation now. He's also credited for discovering the fundamental theorem of calculus, which suggests that differentiation is the inverse of integration. And the time period would show that that was likely after seeing some of the works of Newton as one of his students. Then we get to Isaac Newton, who's considered one of our greatest mathematicians of all time, as well as one of our greatest scientists. He spent a significant portion of his life at Cambridge, starting in 1661 all the way up until 1702, taking breaks only for times when it was closed for the bubonic plague. Often, though, he would not formally publish much of his work because he had scientists attack some of his initial works on optics. And this leads to some of what happens with the different views of the origination of calculus between him and Leibniz. But we know that from 1664 to 1666, Newton's considered to have developed his form of calculus to help him study physics as well as formulate his theory of gravitation. He did not formally publish this work, instead wrote them as manuscripts at 3 different times. His work was not published formally until 1736 after his death. Now, with those lack of formal publications, that's where there becomes the arguments between him and Leibniz as we get into the late 1600s, whereas Leibniz does publish his work and Newton then accuses him of stealing some of the works due to their correspondences in the 1670s. Now, Isaac Newton had a substantial amount of accomplishments both in mathematics and in science, and he probably was one of the major players to significantly improve the way that physics is done to this day. We know that starting in 76, we have a letter that shows him discovering the generalized binomial theorem, although not proving it within that letter to the Royal Society. The Principia is considered one of the seminal works in physics because it established laws of motion and gravitation. And again, that is some of the foundations to our modern physics, especially calculus-based physics. In 1707, his work on Arithmetica Universalis showed significant advancements in theory of equations so that we can recognize that complex roots have to come in conjugate pairs, and that we have rules for determining upper bounds of roots, as well as expanding Descartes' rule of signs to include the number of complex roots. And these are just a couple of the things he did beyond his mathematics and calculus and physics. Now, let's talk about his method of calculus, which we call the method of fluxions, is where he wrote his original manuscript that was eventually published in 1736. Here, he was looking at curves that are created by a movement of a continuous point. He used 2 key terms, fluents and fluxions. The fluent was the quantity that was dependent upon time, and the fluxion was the rate of change of that fluent. Now, when a fluent, which we'll consider x, generates this curve y, then the fluxion of the fluent is y dot. And the fluxion of y dot is y dot dot. In other words, the second derivative. So that's one of the times you'll hear that Newton had the dotists and Leibniz had the deists, because Newton used these dots to represent the derivative. Now, the moment of a fluent was an infinitely small amount by which a fluent increases in an infinitely small amount of time, which we'll mark as naught. And the way that was written as x dot naught. As we're going through his methods, you'll see that any time that this term, x dot naught, is squared or higher power, it becomes virtually 0, so it gets removed from simplifying equations. Now, let's look at trying to actually solve a fluxion here with x squared minus ax plus xy minus y squared equals 0. Newton's method would say let's replace the x's with x plus x dot naught and the y with y plus y dot naught. Now we're going to simplify through expansion. So you see, calculus is a lot of algebra. And really that's all we're doing here is using algebraic methods to simplify. So we're going to expand each of these terms so that we have x squared plus 2x x dot naught plus the quantity x dot naught squared minus ax dot naught plus xy dot naught plus yx dot naught plus x dot y dot naught squared minus y squared plus 2y dot naught minus the quantity y dot naught squared. And all I've done is just expand following algebraic methods. Now what Newton would say is we're going to remove all of our 4 original terms. And we look at what's left. Next, because the naught squared and anything higher becomes virtually 0, he says they're negligible, let's remove those terms as well. And here we have our equation that we can then work with. We're going to divide every term by naught, and that will leave us then just with x and x dots. Now, depending on the work of Newton, he may just solve it to get y dot by itself. But we're going to make it look like something that we would do now in calculus. So let's get the y dot by itself. So we're going to move all the terms with y dot to the opposite side. And then let's use the distributive property to pull out the x dots and the y dots. It helps just see what's going on in this problem. Now we're going to divide both sides by that 2y minus x to get the y dot by itself. And this is a solution that would be provided by Newton. But if we think about what we do nowadays, we would then divide both sides by the x dot, so that we would say that the solution or the derivative would be 2x minus a plus y divided by 2y minus x, and that would be our derivative. Now, Gottfried Leibniz was the other famous mathematician who's considered to be one of the inventors of calculus, along with Newton. He started at a young age trying to create this general universal mathematics that could be done through symbolic logic. And this led to the development of symbolic logic later in the 1800s. But it was based off some of the works that Leibniz created. Now, most of his life he spent as a diplomat. And as he was a diplomat, he was able to go to many different countries. Early in his life, he was able to go to Paris, where he was able to work with Huygens and actually be taught mathematics from him. It was during this time that Leibniz was able to take the mathematics he was learning from Huygens and develop his formula or his formation of calculus. He actually published his first paper in 1684. And you can see that while that is well after we consider when Newton is to have constructed his calculus, Newton had no formal publications at that time, and that's where much of the disagreement comes between these two men. However, while we often credit Newton with developing calculus, it is the work of Leibniz as to what we use both in the symbols that we use for calculus and the way we teach calculus nowadays in our common classrooms. For example, if we look at the original method, and this is why you see the controversy. Here we have an equation, y equals ax squared plus bx plus c. While Newtons were considered the dotists, Leibniz was the deists because they used dx and dy. That should look familiar because that's what we use when we do calculus. So here we're going to replace our x's and our y's with the y plus dy and the x plus dx. Now we're just going to expand. So we get our terms here, and we're going to distribute that a into those three terms so that we end up with y plus dy equals ax squared plus 2ax dx plus the quantity dx squared plus bx plus b dx plus c. Like Newton, we would remove the original terms. Then, like Newton, we would then remove any d term that is greater than a second degree. So you can see again, these are methods very similar to what Newton was doing, but they were developed independently. And it was this similarity in some of these methods that got the large controversy between the two of them. Now we're going to divide both sides by the dx if we distribute it out, and that will leave us then with our derivative, that is 2ax plus b. Now while this is impressive and it's fascinating that he was able to calculate and create this on his own, it's not the original method that we care so much about anymore. It's the modern methods. Again, that focus he had on trying to make things represent symbolically allowed him to think about how can we simplify this in a way that creates rules that are much more useful and relevant in using calculus. Starting with our power rule, where we know that when we take the derivative of x to the n, that will become n times x raised to the n minus 1. Leibniz is also able to construct the constant rule, that we can pull the constant out of a function before we take its derivative, or the sum and difference rule, or the chain rule, as well as the product and quotient rules. These are the modern methods of calculus that we use nowadays that if it wasn't for the work of Leibniz, we wouldn't be doing this in the same manner. And that's what's helped propel calculus so far as it's gone, thanks to the works of Newton as well as Leibniz.